Hello. In this video, we will consider applications of definite integrals specifically related to calculating the volumes by using cross-sections. What's the main idea of this chapter? Well, when we look at using definite integrals to solve different problems, we can solve the bigger problem by cutting them into smaller problems. We can solve those little problems using relatively simple mathematics and summing the solutions to solve the larger problem. For example, suppose we want to consider which loaf of bread is the largest, and let's say that the largest in this case will be by volume. Well, one way to do this is by immersion, but who wants soggy bread? So we're going to consider another way. We're going to find the volume of the loaf of the bread by considering volumes of slices and then adding up the volumes of those slices. So to do that, we're first going to put an axis alongside the loaf of bread, and we're going to identify where we're going to make the slices. So suppose we slice the loaf of bread into n slices, and we're going to slice at points t sub 0, t sub 1, t sub 2, up through t sub k minus 1, t sub k, and t sub n. So here's where I have my cutting points. So I don't need to make a cut right here at the very end, but maybe then at t sub 1 and t sub 2, up through a continuous slicing up through t sub k minus 1 and t sub k until I get n slices of bread. If I make the slices thin enough, any given slice will have approximately the same cross-sectional area at any given point of the slice. So if I look at this slice of bread right here, I see the surface of this bread, of this slice, has a cross-sectional area, and its thickness is given by the width of that slice. Now, since this slice has approximately the same cross-sectional area at any point of the slice, I can consider that slice to be like a prism. And we know how to find the volume of a prism. We simply take the area of the base times the height. In this case, we'll treat the height to be the thickness of the slice. So if I consider this octagonal prism, I've got the area of its base multiplied by its height. Now, for the bread, let's consider that at any point t, the function a evaluated at t gives the area of the cross-section of the bread at point t. So therefore, the volume of the kth slice is equal to the cross-sectional area times the thickness of the slice, which we can say is a evaluated at t sub k times t sub k minus t sub k minus 1, which we also write as delta t sub k. Then to get the volume of the bread, we simply sum the volumes of the slices, which is approximately summation k going from 1 to n of a sub t sub k times delta t sub k. And as we take the norm of the partition and let it go to 0, we get the definite integral from a to b of a of t dt, where a of t is that cross-sectional area function. dt, we're integrating with respect to t because we took slices perpendicular to the t-axis. Okay. Now you'll recall that taking the norm of the partition and letting it go to 0, which is part of the definition of a definite integral. This means that we're letting the widest slice go to 0, which means we're going to get infinitely many slices and very, very, very thin slices. Now let's look at a specific problem involving this process. Suppose we have a solid S, which has as its base the region bounded by the graphs of y equals 2 times the square root of x, y equals negative 2 times the square root of x, and x equals 1. For each x, with x between 0 and 1, the cross-section perpendicular to the x-axis is a square with one edge in the plane of the base. We want to find the volume of the solid. The first thing that we want to do in any of these problems is to draw sketches. We want to consider 2- and 3-dimensional perspectives. It's very important to practice drawing these sketches. It's something that it does take time, it does take practice to acquire that skill. So for each example that we pursue in this video and other videos, I want you to pause the videos and actually sketch what the region is, what the 3-dimensional solid that results would be. Okay. So here we're going to take a look at the graph of the region. So here I've got y equals 2 times the square root of x. And here we have y equals negative 2 times the square root of x. And we're staying between x equals 0 and x equals 1. Okay, so there's a two-dimensional picture of the region. We next want to consider a three-dimensional perspective, and to do that, I've got another graph of the two-dimensional region, and I've got an initial sketch of a rectangle positioned where one edge of the square. Now we want to take a look at the three-dimensional perspective. And to do that, I've got another sketch of the two-dimensional graph of the region, and I've got a square positioned with one edge of the square in that base. So here's one edge of the square, and then, now it doesn't look like a square, it looks more like a parallelogram, but in order to draw three-dimensional, sometimes that's helpful. Sometimes it helps to draw things at an angle, so I'm going to say that this is my y-axis. Here's my x-axis. Here's y equals a positive 2 times the square root of x. Here's y equals a negative 2 times the square root of x. And suppose I draw in my squares. So they're going to look like this. And we're going to see that as we get closer and closer to x equals 1, the squares get larger and larger. And you want to also consider which lines end up being parallel. So for example, if this line is in the base of the solid, this line is parallel to that, so therefore the edges that arise must also be parallel. To get additional perspective, I've also imported images from Mathematica. Here you can see that I have the x-axis right here. The y-axis is back here. And then I would call this the z-axis. Okay. So you can see that I've got the curves y equals positive and negative 2 times the square root of x, and you can see the squares that rise up from that. In this second graph, I've got the y-axis back here. The x-axis passes through the middle like that, and you can see this backside, and you can see the squares, and you can see the curve that results as the corners of the squares rise. And then this third image says if I'm looking at from the positive x-axis right here, I've got the y-axis back here, and you can see those squares. Okay. So now let's take a look at how we actually go about finding the volume of the solid. The very first thing that we want to do is we want to consider the partition of the interval. And since we're taking cross sections that are perpendicular to the x-axis, we are going to partition the interval from 0 to 1 along the x-axis. So our partition is x sub 0, x sub 1, x sub 2, up through x sub k minus 1, x sub k, and then on up to x sub n. And as you recall, with a partition, this leftmost endpoint is always our x sub 0, our initial partition point, and the last point of the partition is always the right endpoint. Okay. And if I note that here in the diagram, I would have x sub 0. This might be x sub 1 up through x sub k minus 1, and this would be x sub k. So then, just as we did before, we're going to find the volume of the kth slice. Delta V sub k is the area of the base times the width of the slice. Okay, well, what's our area? In this case, we're working with a square base. Okay, we know how to find the area of a square, so we simply need to find the length of one edge of the square. Well, the edge of the square sits between the curves y equals 2 times the square root of x and y equals negative 2 times the square root of x. So therefore, this is going to be the length of the edge squared. We're always going to take the greater minus the lesser, the top minus the bottom. So I'm going to say top minus bottom squared will give me the area of that square times the width. And the width is going to come from that change in our consecutive partition points. So this was x sub k minus 1. This is x sub k. So my width is going to come from x sub k minus x sub k minus 1. So the top value comes from inputting x sub k into my greater function. So I've got 2 times the square root of x sub k minus negative 2 times the square root of x sub k. So that quantity gets squared to produce the area of my square. I can rewrite x sub k minus x sub k minus 1 as delta x sub k. And when I simplify this, I'm going to get 4 times the square root of x sub k squared times delta x sub k, which will give me 16 times x sub k times delta x sub k. So here is the volume of the kth slice of the solid. And now I'm going to sum the volumes of the slices and develop a Riemann sum. So I've got that the volume of the solid is approximately equal to the sum of from k going from 1 to n of delta v sub k. And I simply have the kth volume calculated. I can deposit that in for delta v sub k. So the Riemann sum from k going from 1 to n of 16x sub k times delta v sub k, delta x sub k, gives me the approximate volume of the solid. And when I take the norm of the partition as it goes to 0, I get the definite integral from 0 to 1 of 16x dx. And since I took the norm of the partition to go to 0, my slices got very, very thin. So this 16x sub k became 16x. Delta x sub k, the width of my slice, became my differential dx. And because I'm integrating with respect to x, and x ranges from 0 to 1 on my partitioned interval, the endpoints of the interval become the limits of integration. So when I integrate, I'm going to get 8x squared, evaluated from 0 to 1, which gives me a total volume of 8 cubic units. So in summary, after we draw the sketches, we want to partition the interval P. We want to slice the solid and find the volume of the kth slice, a generic slice, delta v sub k. We want to sum the volumes of the slices to develop a Riemann sum, and then we're going to take the limit of the Riemann sum as the norm of the partition goes to 0, which results in the definite integral.